the one where you have the geometries packet, we will start on that. So Jack is recording the class here, and I won't be able to be here 7th period today. So for all you 7th period folks watching this, you're welcome. I don't want you to have to miss out, because you know that's how much I want you guys to learn chemistry. Okay. So first thing, your group needs to come up here, and you are going to grab one of these newer styrofoam balls. This will be your central atom. Grab one of those, and then grab 6 of the smaller ones, okay, and then you need 6 toothpicks, okay? So go ahead and come on up and grab what you need, both of these. Okay, so every group needs one of these. One of these, and then grab 6 of the smaller ones and 6 toothpicks. That. Anyone else see the bigger ones with the central atom? There you go. Okay, grab 6 of the smaller ones and grab 6 toothpicks. You might become a videographer because of this.
I know.
You do such a good job. All right, the focus for today here is we're actually going to start building these molecules, and we're going to go visualize what their shapes are. The older styrofoam balls are not in the best condition. You'll notice as you use them, you'll start poking some of the styrofoam out. That's fine. Okay, we'll clean it up when we're done. All right, what is the first molecule that your Lewis structure for? BEF2. All right, your Lewis structure should look like this when all is said and done. You have your beryllium as the central atom. You should have 6 pairs of electrons left after putting in the bonds. And the beryllium is okay with an incomplete octet. Okay, so this should be your Lewis structure. Any questions on that, folks? Okay, if you don't have that, make sure you get it changed on your sheet there. All right. So what we're going to do now is we're going to start filling out this chart here, and then you're going to build the molecules with the styrofoam balls and toothpicks you have there. All right, when we talk about electron groups on the central atom, that would be any bonds that the central atom makes, and it would be any lone pairs that it has. So how many electron groups do we have on the central atom right now? 2. There are 2. 2 bonds, no lone pairs. So 2 electron groups on the central atom. 2 electron groups. How many atoms are bonded to the central atom? Also 2. Each of these bonds, because it has 2 bonds, it's also bonded to 2 atoms. Okay, so now we're going to work on building the molecule. The large styrofoam ball you have there will be the central atom. Okay, so this will be your central atom. The toothpicks will be the electron groups. Okay, the toothpicks will be the electron groups, and then the smaller balls will be those will be your other atoms. Okay. Now, from the video you guys watched for today, how are these electron groups going to arrange themselves around this central atom? What is the theory you guys read about? Mr. Raymaker behind the camera.
They'll be all equally spread out.
Okay, not necessarily. You're close. You're really close.
It should be as spread out as words. Okay, they should be spread out as far away from each other as possible.
Okay, spread out as far as possible, which typically, Jack, you're right, will mean equally spaced. So, with your partners, get 2 toothpicks, put them in the styrofoam ball as far apart as they possibly can be. Ready, set, go. Now, if there are atoms on the other end of those, then go ahead and stick atoms on the other end. All right. So we have successfully built this one. Everyone hold it up please so I can see it. Okay, this is as far apart as you can put those electron groups. So this is exactly what this molecule actually looks like. Now, we have two different geometries. Two different geometries, you can see it on the chart here. We have what's called the electron pair geometry and the molecular geometry. The electron pair geometry considers all groups of electrons, whether it's bonding or lone pairs. Now in this case, we don't have any lone pairs, so both of these are going to be the same. What shape would you call this? What does it look like to you? Give this geometry a name. What does it look like to you? Okay, it looks like a line, right? We call this linear. So the electron pair geometry is linear, as is the molecular geometry. Because again, there are no lone pairs on our central atom here, so they'll be the same. Okay, we'll see examples here in a bit when they are different. Okay. What is the bond angle going from one bond to the next? How many degrees do I have to go through in order to get that? 180 degrees. That is the bond angle. Now I know there is another column on your sheet there for polarity. That's something we'll get to later. Okay, we're not going to worry about part of our discussion today. Alright, so for every one of these, what you're going to do, once we get the Lewis structure on there, we get the groups written in, you and your group will build the molecule, getting the electron groups as far apart as possible. Okay, and then we'll talk about the names of those shapes on. Okay? Alright, what's the next one, guys?
CO2.
CO2. Alright. Your Lewis structure should end up looking like so, with two double bonds, one to each oxygen. Like so. Any questions on that Lewis structure, ladies and gentlemen? Okay. Double bonds, while we are sharing two pairs of electrons, it still just counts as one group of electrons. This double bond here is still one group of electrons. So how many groups of electrons are on the central atom there? How many groups of electrons on the central atom? Brian? Two. It's still just two. Okay? It's still just two. Yes, that is 4 pairs total, but it's 2 groups. Okay? Because each double bond is still just one group. And we still have 2 atoms on the central atom. Will the geometry be any different than this then? Is it going to be structured any differently? No, it's the exact same thing. These 2 groups of electrons are going to arrange themselves exactly the same. Okay? They're going to arrange themselves exactly the same. Okay? So here the geometry, the electron pair geometry is linear, as is the molecular geometry. Also linear, and we have 180 degree bond angle. Okay? So the point of this one here is just to get us to understand that double bonds don't give us anything different from a geometry point than single bonds do. They're exact same. Okay, what's the next one? BF3. Alright, BF3. What's your central atom going to be here? Boron. Okay, so you may have drawn your basic arrangement like so. How many pairs of electrons are we going to get here? How many pairs of electrons? What do we decide, guys? How many pairs of electrons? How many valence electrons does boron have? 3. How many does each fluorine have?
7.
7. So 7 times 3 is 21, plus 3 from boron is 24. So how many pairs is that?
12.
12 pairs. How many pairs do I use for my single bonds? 3 pairs. So I use 3 pairs there. How many do I have left?
9.
I have 9 pairs left. I start filling the octets of the terminal atoms. How many pairs do I use to fill the octets of the fluorines?
9.
How many pairs do I use? 9. How many electrons do I have left? None. Does everything have an octet?
No.
Well, boron doesn't. Is that okay though? Yes, because it only has 3 valence electrons. So that's it. End of story right there. End of story right there. That's the Lewis structure. All right, how many electron groups do we have on the central atom? 3 electron groups. And how many atoms are bonded to the central atom? Also 3. So again, whenever there are the same number of atoms as electron groups on the central atom, that means the geometries will be the same. Okay, they'll be the same. All right, with your partners, build this molecule. 3 groups of electrons as far apart as possible. All right, it looks like our groups have been pretty successful with this here. Go ahead and hold your structures up there, folks. Okay, so notice, even though you may have drawn the Lewis structure like I did here on the board, okay, a lot of you probably drew it something similar to this, kind of a T shape, that doesn't mean that's the actual shape of the molecule. This puts those electron groups farther apart, doesn't it? Okay, this puts the electron groups farther apart here. And so, remember, the reason that happens is it minimizes the repulsion. Make sure you're getting it nice and tight on the structure here, Jack. So,
The camera doesn't really go up. There we go.
You got it now?
Oh, yeah.
You want me to hold it lower?
Oh no, like I can't move it. Maybe I just got to back up.
Okay.
There we go.
All right, we're good now?
Yep, we're good.
Okay. There we go. Okay. So notice, what would you call this shape? I'll just ask you. What do you guys see here? You see a triangle, so we call that trigonal, but we just don't call the geometry trigonal. Notice the molecule lays flat, doesn't it? It lies all in one plane, doesn't it? So we call this geometry trigonal, because of the triangle shape, planar, because it all sits on one plane. So, the geometry, said, is trigonal planar. Okay. See how it's spelled there? And then the molecular geometry is also the same. Okay. Again, that's because in our molecule, every one of these electron groups has a lone pair, or does not have a lone pair. There's an atom there. Okay, that's why it's the same. What would the bond angle be here between one atom and the next? One group, one bond to the next. Yes, sir. 120 degrees. Yeah, it's 360 around the circle, and we divide it into 3, so that's 120 degree bond angle. 120 degree bond angle. All right, what's the next one? SO2. Oh, we're at the top where it's easier to see. All right. So your central atom will be sulfur. Got a couple oxygens in there. How many pairs of electrons am I going to get here? 18 electrons total, so 9 pairs. I use 2 for my single bonds. So how many do I have left then? 7. Okay, where do I put those 7? At least where do I start with those? On the oxygens to fill the octets. So those take 3 pairs each. Those take 3 pairs each. How many electron pairs do I have left? 1. Where's that going to go? on the sulfur. Does everything have an octet? No, the sulfur's still shorter pair, isn't it? Where is he going to get another pair? Double bond with? Okay, it doesn't matter which one. It'd be the exact same either way, wouldn't it? Now, the point of this here, this isn't something we really cover in this class. I'll show it on the left side here, so I'll erase one of the lone pairs and I'll put a double bond in there. The point is, it's actually not a single bond and a double bond because it's exactly equivalent on both sides. The actual structure is a hybrid between this and the double bond being on the other side, which we call that resonance, and there's a different way of drawing it, which we're not going to worry about. But for our purposes for this is perfectly fine. Okay? We'll just draw like so. Okay? Now does everything have an octet? It does. Okay. How many groups of electrons are on the central atom now? Not how many bonds, how many groups of electrons? How many is this here? Now it's 2 electrons, it's 1 group of electrons. How many is this here? Also 1 group. Okay, it's 2 pairs, but it's 1 group. There's 2, but then we have this lone pair. So there are 3 groups of electrons on the central atom. Lone pairs count as a group. 3 groups. How many atoms are on the central atom? 2. All right. Here's the most important idea from this geometries here. Okay? What determines the basic geometry, or what we call the electron pair geometry, is only the number of electron groups. Okay? This was my previous structure right here. This trigonal planar, because there are 3 groups of electrons. This is still going to be the case. It's still going to have this same basic structure. These 3 electron groups, the single bond, the double bond, and the lone pair, will arrange themselves in the same manner. The only thing that's different is now one of these atoms that we have bonded is no longer there. One of them's a lone pair. Now because these are all equally spread out, it doesn't matter which one I choose. So I'm going to just take this top atom off. So you guys do the same. Okay, the electron group stays there. Jack, can you see the toothpick on there?
Yeah, I can see
Okay.
the toothpick.
The electron group stays there. The electron pair geometry considers all electrons, whether they're bonding or lone pairs. So this basic geometry is still the same, isn't it? What did we call this again? This is trigonal planar. So the electron pair geometry, is trigonal planar. Electron pair geometry is trigonal planar. The molecular geometry only considers the atoms. Now this one's kind of strange. It's angled, isn't it? Okay, or bent. Guess what we call it? Bent. Okay, I know, ingenious. The molecular geometry is bent. Okay, it's no longer a straight line, is it? Okay. The most important thing I can get across to you here, as far as how this relates to the Lewis structure, is we can't simply look at the Lewis structure and say, well, that's linear, because I drew it in a straight line. You could very well draw the Lewis structure just like this, and it's a perfect Lewis structure. But this is not linear, is it? Okay, not linear. Okay, what would the bond angle be here? The angle between these 2 bonds. It's going to be close to 120, not quite though. Because recall, this is now a lone pair up here. Is that going to increase or decrease the repulsion between this lone pair and the bonding pairs? Where is there going to be a greater repulsion? Does this lone pair of electrons up here have another atom to attract to, other than the central atom? No. So these electrons here are going to spread out a little bit, which is going to force these bonds here together just slightly. So here's how we write the bond angle. we simply say it is less than 120 degrees. Less than 120. Okay, it's close to 120 because this basic geometry is unchanged from the trigonal planar, but those bonds get squeezed down just a little bit. Okay. All right, what's the next one, guys? All right. What's the central atom going to be? Okay, central atom will be carbon. How many pairs of electrons do we get? 16 pairs. How many do I use for my bonds? 4. So how many pairs do we have left? 12. Where do they go? On the chlorines to fill their octets. How many pairs will that take to fill the octets of the chlorines? It will take 12. Do I have any electrons left? Nope. No electrons left. So, there they have an octet? We do. Okay, build the molecule. Ready, set, go. Think in 3 dimensions here, folks. Okay? Think in 3 dimensions. Remember, you get all 3 dimensions to work with. Alright, so this one I did show you on the lesson, on the video. So a lot of you are doing a pretty good job of this one. Go ahead and hold them up, guys. We're getting there. Yeah, not bad. Not bad. Okay. So I haven't put the atoms on this one yet here. I will here. So it's not just in a square shape, is it? Okay, because that would not put those groups of electrons as far apart as possible. Okay, we get something like so, don't we? Okay. Now, if you build it just right, and this is really hard to do, just eyeballing it with the styrofoam balls, if you build it just right, regardless of which group you put on top, it should look exactly the same. Notice I did not succeed super great with that. Okay, that's why I got this one here, this model set I have. Okay, so notice the shape here, and the key to trying to do it right is the 3 that you kind of have at the bottom for the tripod, you might call it. They stick a lot farther out than down than you think. Okay, so notice these aren't going very far down. Okay, they're almost straight across, just a little angle down. That way, regardless of which one I put on top, it looks exactly the same. Okay. Again, hard to build, just eyeballing it like that. All right, what shape would you call this?
Pyramid.
Okay, it looks kind of like a pyramid, but we don't call it that. That's a good guess, though. Let me ask you this. If you were to like wrap this thing in a cloth, how many different faces to the shape would we have? There are 4. What prefix do we have for 4?
Tetra.
Tetra, this is tetrahedral. Tetrahedral, because there are four shapes, four sides to the shape, if you will. Now notice, we have both four groups of electrons and four atoms on the central atom. So our electron pair geometry is the same as the molecular geometry. They are both tetrahedral. And the bond angle for tetrahedral geometry is 109.5 degrees. 109.5 degrees. They are all the same distance apart, so it's the same angle. Okay, we get 109.5. All right, let's go to the next one. What's the next one, guys? pH 3. All right, so your central atom will be phosphorus. Okay, how many electrons do we get here? 8 electrons, because 5 from the phosphorus, 1 from each hydrogen. That's 4 pairs. Where do we start with those 4 pairs? You're disappointing your 7th period classmates. Where do we start with 4 pairs, guys? Hey, we put the bonds in. Put the bonds in. How many pairs does that use?
3.
3. How many pairs do we have left? 1. Where does it go?
On the
Okay,
central.
not on the hydrogen. You guys are correct on hydrogen because we don't need any in the hydrogen because it's happy. Okay, so the remaining pairs go on the phosphorus. Just the 1
Yep.
pair we have there. Does everything have an octet?
Yes.
It does. It does. So we're good there. All right. How many groups of electrons are on the central atom? 4. I have 3 bonds and 1 lone pair. That's 4 groups of electrons. Right now, already, I don't even need to know the next part. I could go ahead and write down the electron pair geometry. What is it going to be? Tetrahedral, because there's 4 groups of electrons. They will arrange themselves in the same way. Spelled correctly there. Once we know how many groups are on the central atom, we know the same basic geometry. The electron groups will arrange themselves in this tetrahedral geometry. I'll use the model here to make it easier to see it there, okay? The only difference now is one of these groups is no longer bonded to an atom, is it? So I'll just take one of the atoms off. It does not matter which one because they're all equidistant. Okay, they're all equidistant. So I only have 3 atoms on here. So if we consider only the atoms, we're not considering this lone pair up here, what shape do you see here? Okay, it counts like a triangle, so what do we call that part? We don't say triangle, look back at the previous link you need to. Trigonal. Okay, we call it trigonal, but notice it no longer sits on a flat plane, does it? It doesn't sit flat on the table anymore, does it? I'll move it up here so the camera can see it. It doesn't sit flat on the table. In fact, it kind of has a pyramid shape to it, doesn't it? So we call this trigonal, because it's trigonal, pyramidal, because there's a pyramid shape to it. I know it's kind of a funny name, but that is what it's called. Trigonal, pyramidal. What do you think the bond angle will be here? Remember, it's still tetrahedral in the basic geometry. So what's that bond angle? The tetrahedral. 109.5. But what's this lone pair up here going to do to these bonds? It's going to squeeze them down just a little bit.